Welcome back to part 3 of week 4 in advanced algorithms. We're going to continue from where we left off last time, where, if you remember, we developed the concept of pathwidth, and we did that using this construct called a path decomposition. So recall that a path decomposition is a sequence of subsets of our graph G, which has three properties. The first one is vertex coverage. You want to ensure that the union of all these subsets is the entire vertex set of your graph. The second one was edge representation, where you ensure that for every edge UV in your graph, there is at least some bag in this sequence that contains both of those endpoints U and V. And the third property was vertex coherence, where we said that if you look at all the bags that contain a specific vertex V, then that forms a contiguous subsequence of the given sequence, right? So this was a path decomposition, and we were interested in a path decomposition that has the smallest possible value of the largest bag size. That's what we called the path width of the graph. Now, to go from here to tree decompositions, it'll be convenient to think of the path decomposition as an auxiliary path structure which has bags associated with each vertex of the path. This is quite natural because already what you have is a sequence of bags, so it makes sense to think of this as a path where every vertex has a subset of the vertex set of G associated with it. So note that this path is an independent structure from the graph G, but what connects it to the graph G is the function that associates with each vertex of the path a subset of vertices of the graph G. Okay, so these two notions are completely equivalent, but this perspective of thinking about the sequence as a path just makes it more amenable to generalization. So I'm going to spoil things a little bit and tell you here already that a tree decomposition can be thought of as simply a path decomposition where the underlying structure is allowed to be a tree instead of a path, which gives you more flexibility. You can do more things once your backdrop structure is allowed to be a tree, and the properties that we seek of the decomposition are very similar to what we already know about path decompositions. In fact, the notion of vertex coverage and edge representations carry over exactly as is. We just need to adapt the concept of vertex coherence so that it actually makes sense on a tree, because now we don't have a natural notion of a sub-interval or a contiguous subpath when the backdrop structure is a tree. So that's the one that we need to tweak a little bit. Now we'll get to this formal definition in just a minute, but before that, I want to show you an example of a graph which might help build some intuition for what we are trying to do here. So just like we used the concept of a thin grid to think about what does it mean to generalize from a path-like structure, we want to think about what does it mean to generalize an arbitrary tree-like structure further. So here is a picture which is taken from chapter 10 of a book called Algorithm Design by Kleinberg and Tardosh. In this book, sections 10.4 and 10.5 are focused on tree decompositions and Treewidth, and it's really nicely described. So it's something that I definitely encourage you to cross-refer as we go through our discussions. So what's going on here? So in the first part, we have a somewhat arbitrary looking graph. And in the second part, the same graph has been redrawn to highlight some of the structure that's hiding in there. Now, you probably already have some intuition for why the picture in the middle is a more structured way of looking at the graph on the left. But the picture on the extreme right tries to abstract out the structure that you're actually seeing. So we probably have the sense that the graph here is composed of these little triangles which are interconnected in a particular fashion. So that's what the picture on the right is trying to capture for us. So for instance, this triangle here is denoted over there on the top left. This triangle here is the next one here, and the edge between them indicates that they have the triangles back in the graph have some vertices in common. you can probably already start imagining how this corresponds to the idea of having a tree blueprint that captures our graph by means of having vertex subsets associated with the nodes of the tree, and these vertex subsets corresponding to specific interactions in the graph, hopefully with the nice kinds of separation properties that we've already seen in the context of path decompositions. So if you're thinking along these lines, you'd be exactly right, and you're probably preempting a lot of what is coming up. So with this example in mind, let's go ahead and actually formally define a tree decomposition. So a tree decomposition is basically a tree along with a function that maps to every vertex of the tree a subset of vertices of our graph G. So that would be a tree decomposition of a graph G. It's easiest to think of it as this pair of objects. The first element of the pair is a tree structure. The second element is this function that associates with every vertex of the tree a subset of vertices of our graph G. And we will continue to call these vertex subsets bags. So you can basically think of a tree decomposition as bags that are now organized in a tree-like structure as opposed to a sequential structure. Of course, we don't want just an arbitrary association of vertex subsets with the tree. We want this association to satisfy some properties for it to be a valid tree decomposition, one that will be useful for us to do dynamic programming on later on. So let's just recall the first two properties that we required of the path decomposition because they're going to carry over as is. The first property is vertex coverage. So just as with the path decompositions, we require that the union of all the bags in the tree is the entire vertex set of the graph, which means that every vertex is present in at least one bag. The second property we are after is edge representation. So just like with path decompositions again, what we need is for every edge to have a bag which contains both of its endpoints. So if UV is an edge in the graph G, then there is some bag which contains both U and V. So there is some node T in the tree capital T such that the bag associated with the node T contains both the vertices U and V. So that's edge representation. It's exactly what you would expect. The third and the last property is vertex coherence. And this is the one that, like I said, we needed to tweak a little bit because in the context of path decompositions, what it meant was that if you highlight all the bags that contain a specific vertex U, then it forms a contiguous subsequence of the path. The natural analogy here is that we again spotlight all the bags that contain a particular vertex V, and we look at this set of bags as they appear on our tree T, and we require the set of bags to form a connected subtree. We don't want this collection of bags to be fragmented. Now, it turns out that once you do have a valid tree decomposition that satisfies all these conditions, then you get some really nice separation properties as a side effect, which turns out to be just the thing that you need to prove the correctness of some dynamic programming approaches, as we are going to see. But before we move on, let's just look at an example of a valid tree decomposition for a graph. So this is borrowed from Wikipedia. You can pause the video here if you like to convince yourself that the decomposition on the right, which really corresponds to the following tree structure. So what's shown is the bags on this tree structure actually satisfies all the properties that we need. In particular, you have vertex coverage, you have edge representation, and the image has been color coded to make vertex coherence really transparent. So all the vertices are colored with a specific color, and you can see that each of these vertices, if you were to highlight the bags that contain any particular vertex, for example, let's say you're concerned about the vertex C here, then you can see that that's the subtree corresponding to all of the bags that contain the vertex C. And you can verify this for each of the individual vertices one by one. And that's an example of a valid tree decomposition. Of course, just like with path decompositions, every graph has the trivial tree decomposition where you have just one bag and you throw in all the vertices of the graph into that one bag. So again, typically not a very useful tree decomposition to work with, but a perfectly legitimate one. And that now brings us to the notion of the width of a decomposition. So the width of a decomposition is once again the largest bag that we have, the size of the largest bag that we have with a -1. And again, the -1 is here so that we can say things like the tree width of a tree is 1, which of course brings us to the question of what is tree width. Again, this is very similar to how we defined path width. We look at all valid tree decompositions of a graph and we pick the one which has the smallest width. And that width is called the tree width of a graph. So every time you have a graph and you have a valid tree decomposition for it, the width of that tree decomposition is an upper bound for the tree width of the graph, because you know that you can certainly at least get the tree width down to whatever you got out of this particular decomposition. Once again, it's a little trickier to prove lower bounds where you want to say that the tree width of a particular graph is at least something that you cannot do better than a certain value. That usually requires a combination of different techniques. Sometimes you can argue it from first principles, sometimes you need to appeal to alternate and equivalent characterizations of the concept of tree width, and that's something that we won't be getting into a whole lot here. However, we will look at a few examples where we state the lower bounds as a matter of fact, and there will be pointers in the references where you can go and find out more about how to justify these claims. Before moving on, though, let me make a comment about a formal connection between the tree width and the path width of a graph. So far, I keep bringing up path decomposition, saying many things are similar or inspired or generalized from what we have already seen about path width or path decompositions. But notice that every path decomposition is actually a completely legitimate tree decomposition, because a path in particular is a tree, and the coherence property in the context of trees basically specializes to the contiguous subinterval or subpath property when it comes to paths. So you can hopefully see that every path decomposition is also a valid tree decomposition. And that gives us a relationship between the tree width and the path width of a graph. For some graphs, it turns out that these quantities are actually the same. Can you think of examples where that's the case? Well, I'll leave that as an interesting exercise to think about. But for now, can you see that one of these quantities is a valid upper bound for the other one? Give that a minute. Just make sure that you commit to an answer before we reveal it here. Okay, so the tree width of a graph is at most the path width, because the path width corresponds to a path decomposition, and that path decomposition is a valid tree decomposition. If anything, the tree width might be smaller. It might be possible to do better because you now have more flexibility in the backdrop structure. So you can probably bring it down, but it's never going to be worse than the path width, because if nothing else, you do have the path decomposition, and that's a valid tree decomposition. So the tree width is at most the path width. You can think about what are examples where the tree width is significantly smaller, and what are examples where the tree width is close to or equal to the path width. Those are nice questions to get some practice with these definitions. Now, let's ask the question, what's the tree width of a tree? Okay. I've already mentioned in passing that we want to say things like the tree width of a tree is just 1. So we should challenge ourselves to come up with a tree decomposition for an arbitrary tree where all bags have at most 2 vertices in them. Now, this is going to be similar in spirit to how we developed a path decomposition for a path. We want to put every edge into a bag, and the way these bags will interconnect will be guided by the tree-like structure of the tree itself. So give it a moment here. You have an example tree. You should feel free to draw your own. Pause the video and come up with a valid tree decomposition for your favorite tree, and try to ensure that its width is just 1, meaning that no bag has more than 2 vertices in it. Okay, so here is one way of building up the tree decomposition of this tree. You basically have every edge as a bag of its own, and the way the bags are going to interconnect is based on how these edges are connected in the tree. So if you didn't have a chance to try and work out a tree decomposition for this tree on your own earlier, then I would encourage you to take this coloring here as a hint and try to build out a complete tree decomposition based on this picture here and come back when you're ready. I'm going to make this explicit in just a second. So here we've added vertex labels to all the vertices so that we can refer to them. And notice that I have a tree decomposition on the right which has exactly the same structure as the tree that we started out with. In general, what we are going to do is with each vertex here in the tree decomposition, we are going to look at the edge that corresponds to that vertex back in the original tree and its parent. And we are going to take those two vertices and make that the bag associated with the vertex here in the tree decomposition. So hopefully that makes sense. The idea for coming up with the tree decomposition of a tree is to treat this tree itself as the tree of the tree decomposition, and for any vertex the bag is going to be the two vertices associated with the vertex itself and its unique parent. Okay, the only place where this may not work out easily is the root, because the root does not have an explicit parent. So that's all right. At this vertex, we are just going to position the root and nothing else. Notice that this is a valid tree decomposition. Vertex coverage and edge representation is really straightforward to verify. The only interesting thing to check is whether we have vertex coherence. But think about all the bags that any specific vertex appears in. A vertex is going to be the parent for its children, and it's going to have a parent of its own. So the bags that it is going to appear in are the vertices corresponding to its children and itself. So that is definitely a connected subtree in the tree decomposition that we have here. Just as a concrete example, let's look at this vertex A here and notice that the subtree that it appears in, the connected subtree that it appears in on the right, is this little portion here which has RA, BA, and CA, and A appears nowhere else in this tree decomposition. So you should be able to convince yourself that this is a valid tree decomposition and its width is 1 because every bag has two vertices. And just like we argued for the path decompositions, we know that 1 is also lower bound for any non-trivial graph. As long as your graph has at least one edge, you'll have to have a bag that has at least two vertices to represent that edge. So 1 is indeed the best we can hope for unless your tree has just one vertex. Okay, so the tree width of a tree would be 1, exactly as you would hope and expect. Now here are some other examples that we are not going to justify in detail, but you can try to either work them out on your own or look them up. So the tree width of a cycle turns out to be 2, and here the upper bound follows from the relationship we have between tree width and path width. So we already know that the path width of a cycle is 2, and the same argument tells us that the tree width is 2 as well. Now, we had a first principles argument to show that the path width of a cycle is at least 2. We need to have a bag which has at least 3 vertices. Now, the same argument as is may not work for arguing that the tree width is at least 2, because now you have a more general structure, so maybe you can exploit that to reduce the bag size. But it turns out that because trees don't have cycles in them, more or less the same argument goes through. You just have to be a little more careful about the details. So that's a nice exercise to think about as well. Now the tree width of a T by T grid turns out to be T, and the tree width of a complete graph turns out to be n minus 1 if the graph has n vertices in it. This goes back to the idea that we talked about for path decompositions as well, that if you have a vertex set that's fully connected, that is all the edges are present, then you cannot completely separate them. There must be a bag that contains all of these vertices. And if the graph itself is complete, then really the trivial tree decomposition is effectively the only one that you have. You could come up with other tree decompositions, but they're all going to be superfluous because there is going to be one bag that contains all the vertices, and then you might as well just have that bag, nothing else. Okay, so those are some examples. Let's now move on and talk about some separation properties that tree decompositions have. So first we are going to talk about separation along an edge. So let's pick an arbitrary edge in the tree associated with the tree decomposition. Let's call this edge AB. And let's look at what happens when we remove the edge AB from the tree. When you remove an edge from a tree, the tree falls apart into two subtrees, one rooted at A and the other rooted at B. So let's call these pieces TA and TB. And in the graph, let's look at the vertex subset A, which is all the vertices that appear in bags in TA, and B, which is all the vertices that appear in bags of TB. We want to claim that AB is a separation, with the separator being the intersection of the bags XA and XB. Okay, so we want to say that the vertices that are common to XA and XB separate everything else in A and B from each other. Now, I'm not going to explicitly prove this, but the idea is very similar to what we did when we were thinking about path decompositions, where we again separated along a place in the middle of the path. So you can think of this as a generalization of that idea that we had for paths. Again, the proof is along similar lines. So, for example, the first thing about a separation is that A union B is the entire vertex set. This is true once again because of vertex coverage. We know that A union B is the union of all the bags, and that's the entire vertex set. Now we want to talk about the actual separation properties. So we want to say that there are no edges that go from A minus B to B minus A. Now assume for the sake of contradiction that there is such an edge, then by the edge representation property, there must be some bag that contains this edge. Now that bag is either here or there. It must be either in TA or TB. Now let's say, for example, that this bag is in TA. And we also know that there is some bag in TB that contains the vertex B. So this is by assumption. So if we make this explicit here, let's say we have U in A minus B and V in B minus A. So we're basically saying there is some vertex in the union of all the bags in the subtree TA, but not in the intersection, because we are looking at A minus B. So the intersection of A and B is gone. So it's not common to A and B. And there is some vertex in B minus A, likewise exclusive to B, not in the common intersection. And there is an edge between them. And let's say here is a bag that represents that edge. It contains both U and V. Now, you know that V is sitting in some bag in T sub B by definition. And you can now apply vertex coherence to say that, look, there must be some subtree. The set of all bags that contain the vertex V forms a connected subtree. And the only way that can happen is if V belongs to the bags associated with the vertices A and B, because that's the only way you can have a connected subtree that captures all the bags that contain the vertex V. So that's essentially your contradiction, because now you have spotted the vertex V in the bags XA and XB. So that must in fact be a part of the separator. It cannot be sitting isolated in B minus A as we assumed. So that's kind of the idea of the proof. Once again, notice that we use all the properties of a tree decomposition: vertex coverage, edge representation, and vertex coherence, just as we did earlier when we were proving a similar theorem about path decomposition. Let me also talk about another interesting separation property, which is vertex separation. So let's delete a vertex from our tree this time. Let's say this vertex is T. And when you remove a vertex from a tree, once again, the tree splits up into a bunch of subtrees, one for each child of the vertex T, right? And so let's denote these subtrees T1 through TD. And once again, let's look at the graphs associated with these subtrees. So we go to our graph G and we collect all the vertices that appear in bags of T1, but then we remove all the vertices that correspond to the root bag, which would be xt. So that is GT1 minus xt. So GT1 is notation for, let's go back to our graph G, of which this was a tree decomposition, and let's pick up all the vertices that appear in bags of T1, which is the first subtree that we got when we deleted the vertex T from the tree. So that's GT1, and from GT1 I remove the vertices of xt, which is the vertices that were sitting in the bag of the vertex that was deleted. Okay, so that's the first subgraph that I want to look at. The second subgraph would be GT2 minus xt, and so on. So I have these subgraphs here, one for each subtree that I get when I remove T from the tree decomposition, from the tree of the tree decomposition. And the claim is that these subgraphs don't talk to each other. They're completely independent of each other. There are no vertices in common and there are no edges that go across. And again, I won't be proving this explicitly, but let me just give you some intuition for what might be going on. So let's say for simplicity that T just has two children, T1 and T2. And once again, let's just try to argue that when you look at the graph, GT1 minus xt and GT2 minus xt. Now let's argue that these two graphs have no vertices in common. Okay, so every vertex that's common to GT1 and GT2 must actually be in xt. Okay, so once you remove xt, there is nothing left that they share in common. Well, suppose not. Suppose GT1 minus xt and GT2 minus xt have a vertex v in common. That means that v belongs to some bag in the subtree rooted at T1 and v belongs to some bag in the subtree rooted at T2. And because of the tree structure of the tree in the tree decomposition, we know that there are unique paths from these bags back to their respective ancestors T1 and T2. But now we can apply our concept of vertex coherence to say that, well, let's look at the subtree corresponding to all the bags that contain the vertex V. That subtree must necessarily contain the vertex T, because that's the only way to connect a bag that is in the subtree T1 with a bag that is in the subtree T2. Because if there was some other way of connecting it, then notice that these parts here combined with any other way that we have of connecting these bags will form a cycle in the tree, which would contradict the tree structure of the tree, right? So it must be the case that the bag xt contains the vertex v. So everything that's common to GT1 and GT2 is actually in xt. So xt gives us, in some sense, a separation between these two parts. And more generally, if you have more children, you can argue along the same lines by taking any pair of them that they don't share any vertices in common. Now, you can also argue that they don't share any edges in common, again, using reasoning that was similar to what we saw back here. You can combine edge representation and vertex coherence to see that you get a contradiction if these parts of the graph have an edge going between them. So you should be able to arrive at a contradiction simply using the properties of a tree decomposition. And we'll see that the reason we really care about these separation properties is the fact that they really help us build up reasonable dynamic programming solutions to problems that we are interested in. If you think about the correctness of the maximum independent set dynamic programming solution that we saw on trees, the correctness really follows from the fact that when you are at any vertex of a tree, if you look at all your child subtrees, there are no edges that go between them. That is why you can take the union of the best independent sets that you get from all of these smaller subpaths and combine them and be assured that you still have an independent set, because there are no edges going across these paths. Now, this is not just true for independent set, but in general, when you're trying to combine solutions to any problem, the fact that you have this sort of a separation means usually that you can combine solutions in a very reasonable way without having to worry about, in some sense, information leakage across these paths. So all the combination, all the commonality is at the bags in some sense. And at the bags, your DP is typically going to brute force and explore all possibilities. So we are going to be fine there by exhaustive search. And the fact that once we are in the process of doing our exhaustive search, in each snapshot, we are going to be looking for the best extensions we have from the individual parts, and we get to combine them. The fact that we can combine them, that luxury is afforded to us by the separation properties of these tree decompositions. Now, this will become clearer as we actually explore concrete examples of dynamic programming. So in the videos, we are going to continue exploring independent set because we have that as a running example throughout. So I'm going to show you in the next video how we can do dynamic programming over a tree decomposition of width, let's say k, to find the maximum weight independent set in a graph. And this description will be based on the description that's there in section 10.4 of Kleinberg and Tardosh algorithm design. And in the video after that, we are going to do the same problem and again over graphs of bounded Treewidth, but using a structure called a nice tree decomposition, which is a tree decomposition with some additional properties which we can actually get for free. And we'll see that this helps us structure our dynamic programming solution in a very clean way, and it sort of leads to a pattern that you can apply for many other problems as well. It's just a convenient way of thinking about DT over graphs of bounded Treewidth. And in case you've had enough of independent set, then watch out for the assignments where you will have a chance to practice some other problems over graphs of bounded Treewidth. So I'm looking forward to seeing you in the next video where we will develop our first DP-based algorithm over graphs of bounded Treewidth.